Most modern electric vehicles are sold as clean machines, but under the chassis, they rely on a hidden network of mechanical friction and fluid plumbing. Even standard production EVs required over 10 liters of hazardous liquids to function, relying on complex loops of chemical coolants, hydraulic brake fluids, and windshield washer reservoirs. Automotive engineering prioritizes extreme performance metrics like 0 to 60 acceleration and top track speeds. These are unusable in daily traffic and come at the direct expense of long-term mechanical reliability. The Zero Fluid Simple EV, or ZF-SEV, is an engineering blueprint designed as a direct counter-response to this engineering misalignment. As detailed in this specification document, the ZF-SEV targets a true 0.0% liquid consumable infrastructure, engineered to eliminate routine maintenance. The platform targets a functional lifespan exceeding 300,000 miles. The only acceptable wear items are the tires and a cabin air filter. To achieve this, the architecture converts every mechanical, hydraulic, and friction-based subsystem into a direct drive software service. This approach removes roughly 80% of the physical failure points found in a conventional vehicle. Achieving fail-safe reliability requires abandoning the performance-first mindset. It requires removing the components designed to force consumers into cyclical dealership service visits. Look at the baseline chassis wireframe of this platform. You will notice an intentional absence of any fluid reservoirs. The traditional glass clearing system is gone. There are no wiper blades, no fluid pumps, no washer reservoirs, and no plumbing for chemical deicers. Instead of liquid, the windshield utilizes surface acoustic wave, or SAW, piezoelectric transducers. These transducers are bonded to the perimeter of the glass. They vibrate at 15 to 30 kilohertz, causing rain droplets, mud, and road film to instantly atomize and disperse sideways across the surface. For chemical and liquid thermal de-icing, the platform utilizes a high-velocity air blade system. High-efficiency ceramic blowers force warm cabin air across a micro-slit at the base of the windshield. Condensation and surface frost are cleared rapidly through targeted kinetic force. By substituting fluid dynamics with acoustic vibration and kinetic air force, the vehicle severs its reliance on seasonal liquid consumables. Moving down to the propulsion architecture, the design lacks a centralized transmission or reduction gearbox. It removes all friction-generating drivetrain components, including differentials, drive shafts, universal joints, and CV boot seals. Propulsion is handled by 4 independent, low-stress electric motors, each assigned to an individual wheel. These motors are not housed inside the wheels. They are mounted inboard on the chassis frame, driving the wheels through short, direct drive spindles. This placement protects sensitive electronics from road impacts. Each wheel operates on a modular corner pod concept. All 4 assemblies, motor, spindle, bearing, and controller, are identical. This enables a 15-minute replacement cycle. If worn or damaged, unified structural bolts and quick disconnects allow a technician to swap the entire unit using standard hand tools. True modularity is an economic strategy that eliminates asymmetric inventory costs and bypasses specialized labor bottlenecks. At the wheel hub, physical friction brake pads, rotors, hydraulic calipers, and brake lines are absent. Stopping power is executed 100% through software-controlled motor magnetic modulation, adjusting the magnetic fields at sub-millisecond rates. Without a mechanical hydraulic backup, the system must safely decelerate even if the battery is full and cannot accept regenerative power. When the main battery is at a 100% state of charge, the regenerative braking current is automatically diverted to an underbody passive resistive heatsink to maintain full stopping capacity. The ultimate edge case is a total high-voltage power loss while the vehicle is traveling at speed. To solve this, the platform utilizes back electromotive force, or back EMF, emergency braking. In the event of power loss, automated contactors instantly short the motor phase windings across passive resistive loops. The vehicle's forward kinetic motion forcibly spins these shorted windings, generating massive electromagnetic drag. The physical inevitability of this reaction abruptly and safely halts the wheel rotation, bringing the vehicle to a controlled stop without any active electrical power. Passenger safety is guaranteed by the immutable laws of electromagnetism, forces that, unlike hydraulic brake fluid, cannot leak or degrade. Once stopped, the system must hold the parked vehicle stationary, without relying on handbrake cables or electronic servo calipers. Each wheel hub features a mechanical, zero-wear permanent park pin system. The default state requires zero electrical power. When turned off, heavy mechanical springs aggressively push a high-tensile steel pin into an internal hub gear slot. Electromagnets only consume power to pull the pins back against the spring when the driver actively enters drive mode. On steep hills, the weight of the vehicle places a side shear load on that pin. To prevent binding, the motor applies a millisecond pulse of microtorque to counter the slope's gravity, allowing the electromagnet to retract the pin effortlessly. Beyond stationary hardware, the vehicle's software manages driving faults through a yaw torque elimination protocol. If a single motor experiences a fault, like a thermal spike, the central processing unit instantly cuts power to the opposite motor on that axle. This symmetrical power cut prevents dangerous pulling or uncontrolled spinning. The vehicle shifts into a balanced two-wheel drive limp mode, maintaining steering authority and braking control across the active wheels. By anticipating physical forces, whether countering gravity on a parking pin or balancing yaw momentum, the software preserves the mechanical integrity of the entire platform. When we step back from the individual subassemblies, we can evaluate the measurable impact this zero-fluid architecture has on overall vehicle lifecycle costs. This comparative matrix illustrates the functional difference between standard production EVs and the ZF-SEV concept. Standard electric vehicles maintain over 20 failure points and require flushing more than 10 liters of operating fluids. The ZF-SEV reduces liquid consumables to 0 liters, removes friction braking hardware, and leaves only tires and a cabin air filter as routine wear. Removing these legacy subassemblies is the only physical method to guarantee a 300,000-mile operating lifespan without cyclical dealer servicing. Designing vehicles for extreme track speeds requires complex friction and thermal systems. Those systems are incompatible with extreme long-term reliability. Engineering progress is the elimination of the hardware that eventually fails. Absolute utility comes from stripping a vehicle down to its essential, unbreakable core.